Hi, I'm Jonathan Aldrich, and today we're going to talk about specifying syntax using context-free grammars, derivations, and parse trees. So regular expressions, which we studied last time, are great for describing tokens. Tokens are the smallest meaningful unit of syntax, things like numbers, symbols, keywords, and identifiers. These constructs don't really have any interesting recursive structure, they're just sequences of characters. But real programs do have recursive structure. So consider an expression like 2 times x plus y divided by 3. There's some structure here, right? It's actually shown by the parentheses. We're going to divide y by 3 and then add x to it and then multiply it by 2. And so this recursive structure means that we have one expression inside another, which means we need to define expressions in terms of themselves. So that's recursion. And to capture this higher level syntax with this recursive notion of definition, we need what's called context-free grammars. So here is a grammar for a calculator expression, and you can see that it's recursive. So an expression for our calculator can be, first of all, an identifier like x or y. It can be a number like 3 or 4 or 5.6. It can be a negative number or a negation of an expression, so minus expr. It could be a parenthesized expression, and it could also be expr op expr, right? So an op could be one of the arithmetic operations, plus, minus, times, and divided by. So we can have, 3 plus 4, right? And so here, notice that when we add two things with an operator, those things are expressions themselves. That's the recursive definition where expression is really defined in terms of itself. So we're going to define context-free grammars in something called Backus-Naur form. Okay, and so looking at this grammar we just used, let's define some terms that'll help us talk about grammars. So first of all, we have productions. Here we have two productions, the expr production and the op production. And so the production tells us that something called a non-terminal at the left, here are some non-terminals, expression and op, are defined in terms of the things on the right. So notice that non-terminals can appear, they always appear on the left-hand side of a production, but they can appear on the right-hand side as well. We also have terminals, so things like identifiers and numbers and symbols like divided by or times are all terminals. Those are basic tokens. And then we use the word symbol to talk about either terminals or non-terminals. Finally, we have a start symbol, which we usually denote as S, which is what the whole grammar starts with. So for calculators, we want to talk about expressions, and so expressions will be our start symbol. Where does this term Backus-Naur form come from? Well, in fact, that's two more programming language people. So John Backus and Peter Naur defined the BNF notation, which bears their name, to specify the grammar of ALGOL 60, which was an influential early programming language. John Backus was also the inventor of Fortran. He worked at IBM Corporation for most of his career and was named an IBM Fellow. He also received the ACM Turing Award in 1977. Peter Naur spent most of his career at the University of Copenhagen, where he established computer science as an academic discipline throughout Denmark. And he received the Turing Award in 2005. Let's look at the meaning of context-free grammars. A context-free grammar generates a string. And so we can start with our context-free grammar and use it to refine that grammar gradually into a calculator expression. In this case, we're going to take something that would describe the formula for a line, right? Slope times x plus intercept would be the y dimension of a line. So here we have a derivation. We're going to start with expr, and we're going to break it up according to one of the productions, or one of the options in the productions of the grammar. So first, we'll take the expression and we'll turn it into expr op expr, because that's the last case of our derivation here. Okay, so here you see an expr. One of the possibilities is expr op expr, right? So we're going to turn expr into expr op expr. Now I'm going to choose one of the non-terminals on the right, in this case the second expr, and I'm going to use another production. In this case, expr can be an ID, right? So we'll turn the expr down here into an ID, and then we'll turn the op into a plus using one of the productions for op. And then we'll take the first expr and turn it into another expr op expr, right? Because now we have to do slope times x. And so then we'll refine the expr into an ID, which will be x. We'll refine the op into times, and we'll finally refine the first expr into an ID. And now we have ID times ID plus ID, okay? Now these are all identifiers. It turns out they're going to be different identifiers. In practice, one will be slope, the next one will be x, the next one will be intercept. So each string of symbols along this path from the original expression to the final expression that we have is called a sentential form. Okay, so those are strings of symbols. They could be non-terminals and terminals. But when we get to the end, we have only terminals because we're done deriving this expression. And that's called the yield of the derivation, right? So we start with expr and we apply a number of these productions, one after another, until we get a final sentential form that has only terminals, and that's the yield. So we can use a parse tree to show how a string was derived. Here is a parse tree for slope times x plus intercept, right? We took an expression, we turned it into expr op expr. We took the expression at the end and made it into an ID, intercept in this case. We took the op, made it into a plus. We took the left expression and made it into another expr op expr. And then those became ID, the slope, times, and then another identifier for x. Now, interestingly enough, we could use that same grammar to produce this slope times x plus intercept in a different way, right? We could take the original expression and break it up into expr op expr, but this time we could refine the first expr into ID and then a times, and then the last expr could be, you know, the ID plus intercept. Now, it turns out this parse tree is actually unintended, right? Because what it's doing is it's grouping the x plus intercept together, right? And we know from mathematics that we'd like times to have a higher precedence, right? We want to compute slope times x first and then add the intercept earlier. What this means is that the grammar we had before is ambiguous. It can be used to produce the same string in two different ways, depending on whether we group the slope with x or we group the x with the intercept. So if we're a little bit more careful about the way we write our grammar, we can produce an unambiguous one. So here's a grammar that encodes the usual notion of precedence for mathematical expressions. This one is unambiguous, so any string that can be produced with this grammar can only be produced one way, with one derivation tree, basically, and it captures precedence. So here, what we've done is I've broken up expression into expressions, terms, and factors. So an expression is either a term or it's an expression and then an add operation with another term. So term encapsulates all the things that are multiplications or below. And you notice we also capture the order of operations, right? So if we have an addition operation, an expression has to go to the left. That means we're going to add up all the things on the left first, and then if we have additions or subtractions, we'll do the last addition last, right? Similarly, a term that captures multiplication and division is a term multop factor or a factor. And the factors are just these unary things like a single identifier, a single number, a negation of some factor, or a parenthesized expression, right? So parentheses allow us to go back up and nest an addition inside a multiplication operator or a term. And now, of course, we have to group the add operators with each other and separate them from the multiplication operators so that we can distinguish the precedence of these two. So let's go back and use the improved grammar, and you can see we get a more complicated parse tree. It has more levels, but it's ambiguous this time, right? So it turns out if we want to parse 3 plus 4 times 5, The only way to do it is to make an expression at the top level which has an add-op in it. The left-hand side is an expression, which is a term, which is a factor, which is the number 3. In the middle we have add-op plus, and then on the right we have a term, which is term multop factor, and then we get 4 times 5 out of that. Okay, so that gives you the idea of parse trees and context-free grammars. Let's do an exercise. So here, what I want you to do is we want you to take the expression I already gave you and add and or to this grammar. So we want these to be left associative, just like addition and multiplication. So we'll always compute the thing on the left, the leftmost operator of the same precedence level. And we want a precedence where plus is higher precedence than and, which is higher than or, right? And multiplication, of course, is higher than plus. So look at the pattern that we used for defining addition expressions, addition and multiplication expressions here, and see if you can extend it to make it work with and or. All right, as you can see, the pattern just continues. Next time, we'll talk about implementing scanners to capture the tokens in a language.